Hmm. So today's lecture is on the chapter 4 and the on the of this book, truncation errors and the Taylor series. Okay. Uh, so in this topic, we will be talking about the another type of error, which is called as the truncation error. Uh, it is not to be confused with the truncation process. Truncation process uh, is sometimes in some software or some we use this type of term. For example, in Excel, that when a digit is when a number is truncated, but this is different. This is called as the truncation error. Uh, in that type of error, we don't use all the terms which are needed to calculate a quantity or calculate a number. Okay, so that's why its name comes as the truncation errors, and it is related with the Taylor series in that way, because when we take a function or take a number uh, and represent it as a Taylor series. So then we can come across this type of concept or this type of idea of the truncation error. Uh, so because the Taylor series have various terms, some of the terms you may include, some of the terms you may not include. So as I just told that in that case, including not including some of the terms that will include that will make the error in the calculation to be a, like we are truncating some of the things out from the number. So that's why the name truncation error. Okay, so as a start, non-elementary functions such as trigonometric, exponential, and others are expressed in an approximate fashion using Taylor series when their values, derivatives, and integrals are computed. So it is customary, uh, I mean, in the mathematics field, we can represent uh, uh, not just the elementary, but the non-elementary, not just the non-elementary, but even the elementary functions as Taylor series. Okay, so and some of you may have come across the Taylor series in your previous calculus and algebra courses. Here we will have a short review of this series as well. Okay. Any smooth function can be approximated as polynomial. So Taylor series provides a means to predict the value of a function at one point in terms of the function value and its derivative at another point. So what is this? So this is the main mechanism and idea behind the Taylor series. The Taylor series converts a function into a polynomial. Okay, so of course a polynomial into polynomial is very trivial thing, but a non-polynomial function such as the trigonometric and other exponential functions can be approximated into a polynomial, and then the terms in that polynomial, which is the Taylor series, the terms in the polynomial series are represented by the derivatives, okay, of that function, the value of the derivatives of that function at certain point, and then that function is derivated at some other point. Okay, so this is the some explanation of the Taylor series in words. So let's see in the form of the symbols how the Taylor series look like. So as you can see that the Taylor series look like this. Okay, of course there is more journal form of the Taylor series, but the a rather simplified form of the Taylor series looks like this. So in this case, you can see that we are calculating the function at some argument xi plus 1, okay, xi plus 1. And uh, uh, then what we are doing over here is that we are going to calculate it. So then we calculate that function at this argument xi, okay, and then we calculate the uh, this function, the derivative of that function at uh, then we calculate this derivative of this function, okay, at this at this argument at xi, and then we multiply it with the h, okay, and h is the difference, okay, between xi and so for example, okay, if we want to xi plus 1 and xi, okay, xi plus 1 and xi, h is the difference. That means the next term from x, okay, and then we use the second derivative, okay, and second derivative, and then you have the third derivative, and then up to the nth derivative. And for each derivative, you divide by the same number of the factorials. F3 divided by the 3 factorial, and then nth derivative divided by the nth factorial. And plus the last term is the term, it is called as the Rn, okay? Rn is the remainder, anything which is remaining for this equality to hold true. So Rn is calculated as like this. Rn is equal to f, one more derivative, that means fn, and then the next derivative multiplied by the h power n plus 1. Okay, so h square, h cube, and then h power n. So that means hn is kind of like a so this Rn is like a kind of like a term, which is the next term after this last term in the Taylor series in the derivative, and then divided by the n plus 1 factorial. I think there should be a correction over here. It should be n plus 1 whole factorial. Okay, n plus 1 whole factorial. Yeah. And over here, there is a term which is called, a Greek letter, psi. It is spelled in English as xi, okay, and it is pronounced psi, okay, psi. So multiplied by psi. So psi is uh, is an average value of the function over a period from n and n plus 1, okay, and then so that the total area under that total area under that curve from n and n plus 1 is equal to that psi times the interval of that function. So only this is the definition of the psi. Okay, so here then you can see that the h can be called represented as h is equal to xi plus 1 minus xi. Anyway, so this is a kind of like a boring description for the Taylor series. What you need to know is that you can use this Taylor series to approximate the functions, okay, to approximate the functions. So for the, when we talk about the approximations, so then we talk about the gradual degree of the gradual order of the approximation. So the approximation starts from the zeroth, at the lowest level, the approximation is called as the zero order Taylor series approximation, which only takes the first term of the Taylor series. Okay, if you just take the first term of the Taylor series, so then that approximation will be the zeroth order approximation. And then here you can see that we are representing it by the approximately equal sign, not exactly equal sign. Here we are using the exactly equal sign because we are also adding the remainder, the conceptual remainder term over here. So since we want to use this Taylor series for the approximation, so starting from the lowest level of the approximation, this is the only, this will only use the first term of the Taylor series. First order Taylor series approximation will include the first two terms. Okay, as you can see, the first two terms. And the third order, second order approximation will use the first three terms. Okay, so more the number of terms we will use, more closer will be the answer to the reality, and it will be you can say that the more accurate or less error, there will be less error in the answer, and so on. So if, for example, if you want the third order Taylor series approximation, then we will need to take the 1, 2, 3 first four term of the Taylor series. So this is how you approximate the various values using the Taylor series. So after that, we will look at one example. So do you have any question?
No.
Okay, so we look at the example 4.1 from this book chapter. Use the 0 through 4th order Taylor series expansion to approximate the function this. So although in this case, this function which is given over here, we don't really need to approximate it because it is a polynomial function, and we have the methods available to exactly calculate it. But just to illustrate the method, uh, we will approximate it. Okay. So as I have just told that for the we have to approximate this function from the 0 through the 4th order. Okay, from 0 to the 4th order. So uh, for the 0th order, we will take the first term of the approximation. For the second first order, we will take the first two terms of the Taylor series, and so on. So in this case, as a solution, first of all, our first step will be to find the true value. So true value we can just find by just inputting these values. So what we have to do is we have to evaluate this function at the value of x is equal to 1, at the value of x is equal to 1. Given that starting from the approximation for this function at x is equal to 0. So that means for this kind of for these kind of questions, not only for this question but for some other questions, is that you will be said that the value of this function at certain point is this. Find the value of this function or approximate the value of this function at some other point. So in this case, we are assuming that we know the value of this function at x is equal to 0, which is obviously, if we put input 0 over here, the value of this function will be 1.2. Now we have to calculate the approximate the value of this function at x is equal to 1. Okay. Uh, so so for this, for our comparison purpose, maybe we can, first of all, we can find the true value. Of course, we cannot find the true value for certain unknown functions. Okay. But since it is a known, very well known function, we can find the true value. But this true value will be only used for the comparison purpose. So in this case, if we will just put x is equal to 1 over here and then evaluate it, then it will be the value will be 0.2. So because all the terms will be like this, minus 0.1, minus 0.5, minus 0.25 and 1.2, that will be equal to 0.2. Okay, so the next step is the what actually was asked. So first we will find the zeroth order approximation. So for the zeroth order approximation is just the first term of the Taylor series. Okay, it is just the first term of the Taylor series over here, as you can see, first term. So first term of the Taylor series is the value of the function at the given point. Okay, the given point is x is equal to 0. Okay, so given point is x is equal to 0. So for at that point, we know that the value of the function is 1.2, because if we put 0, 0, 0, 0 over here, only value remaining is 1.2. So this means that our first approximation, that means zero order Taylor series approximation, will be 1.2. Okay. So in this case, it means that the true value of the function we already know is 0.2. The approximated value is 1.2. So 0.2 minus 1.2, that is minus 1.0. So that will be the true error. Okay, so you can even find the true relative error or true relative percentage error, but that is just optional. So here we have just, in this example, we have just found the true error. Okay, so you can so now we can see that by the zero order Taylor series approximation, we have a value of 1.2 and a true error of -1 in this case. Okay, so next we need to find the because we have to find from the first through the fourth order Taylor series. So for the first to the fourth order Taylor series, as you can see from the formulation, we need the derivatives. Okay, in the first order, we need the first derivative. In the second order, we need the first and the second derivatives. So before we find the approximations, let's find the derivatives first. Okay, so that means derivatives are needed for higher order Taylor series approximations. So in this case, we can see that the first order, first derivative will be, so what we can do is, from your knowledge of calculus, you can find its first derivative is equal to minus 0.1 times 4, that is minus 0.4 x cube, minus 0.15 times 3, that is minus 0.45 x square. And then this means be minus 0.5 times 2 is will be 1 minus 1, and then it will be minus 0.5 x, and then the powers will be x cube, x square, x, and 0.5. So remember that this course has a prerequisite of the calculus. Okay, so you should have some prior knowledge of some calculus uh, before applying, before using some of the concepts in this course. So of course, this type of calculus is very fundamental for understanding this course as well. And you can see that you need to take a derivative of this function. Okay, so we have found the derivative function there, and the next step will be to evaluate this derivative function at the given value of x is equal to 0. So at the given value of x is equal to 0, it will be minus minus 0.25. As you can see that if you put x is equal to 0, so it will remain as minus 0.25. So since we have to go up to the fourth order, so we have to take the successive derivatives. So the second derivative by the same way will come from the first derivative. So it will be 3 times minus 0.4, 2 point minus 0.5, and like that. So the last, in this case, that the last term will just vanish, because last term is the constant. And similarly, we will evaluate this second derivative at a value of 0 is -1. Similarly, you can see that we can find the third derivative. Okay, so now the process is quite straightforward and quite systematic. And you can see that the fourth derivative is like this. So for example, fourth derivative will come from the third derivative. So for example, third derivative was this, minus 2.4x. So it will, and the fourth derivative will be minus 2.4. Yeah, a constant value. So f4 at 0 will be minus 2.4. So now we can apply these successive approximations. So the first order approximation will be then, because we know that the first order approximation will be equal to this formula. That means the first two series of the Taylor series. So it will be 1.2. F prime was we earlier we calculated it was minus zero point 0.5, and the value of h was 1. So value of h is uh, the difference between the x values, the difference between the x values. Okay. uh, Remember that in this case, uh, uh, xi and xi plus 1, this is not the difference between I plus 1 and I. It is the difference between xi plus 1 and xi. Okay. And xi plus 1 just shows that it is the next term. Okay. From I. Okay. So it can, so therefore the difference between them can be any number. Say here this here we are, just for simplicity we are taking a no, here no, not for simplicity, here we are taking a difference of just 1. So that means if we know the value of 0, what is be the value of, what will be the value of at 1. We can even take this difference as 0 0.5. So in that case we will be determining the we will be evaluating this function at x is equal to 0 0.5. So in this case, then xi plus 1 will be 0 0.5. Okay, so that is just a uh, side comment for this calculation. Anyway, the value of h is equal to 1, all which is already basically identified, but the value of h can be any number, depending on the what you want to calculate. So that is the first order. So first order will be then 0.95. Okay. So 1.2 and then it will become as 0.95. So this means that the error will be 0.2 minus 0.95. It will be minus 0.75. In this, so by the same way, the second order approximation will include the first 3 terms of the Taylor series. So many of these calculations will be repeating. So in this case, you can see that the first 2 terms will be the same, okay, as we have already calculated. Only there will be the addition of the extra for a third term. So earlier we have already calculated the f double prime, which is equal to -1. So we will just input this value. The value of h we already know. And you know that, remember that the value of h will increase in power. So h from h is equal to 0 to h is equal to 1, sorry, h, the power of h is equal to 0 to power of h1 to power of h2. Okay. So in this case, the power of h will be 2. So with this, the second order approximation will be 0.45, and then the error will be 0.25. So this, you can see that the error is gradually reducing. Error is gradually reducing. So, so now we have done the 0th, first, second order approximation. So we can calculate the third order approximation. But in this case, I have just simplified the calculations, because you know that for the third order approximation, now we can very confidently say that the third order approximation will be equal to the answer from the second order plus the plus this term, okay, which is the this is this third derivative times this. So it simply input the values. So we already calculated these values for the third derivatives, input these values, and then in this case you will see that the third order approximation will be 0.3, and the error, remaining error, will be now minus 0.1. So error is reducing. So you can see that more terms of the Taylor series we are including, less and less the error we are obtaining. And similarly for the fourth order approximation, so we can simply use the result from the third, from the previous term, and then add one more term, okay, into that. So then it will be 0.2. So in this case, incidentally, the error is 0. That means we are getting exactly the true value. So which is of course understandable, because polynomials are actually polynomial functions are the exact representation of the Taylor series. Okay, so this is how the process goes. for the approximation with the Taylor series. So I have tried to explain this process in a little bit of the details. So you can see that the main concept is that you have to calculate the derivatives of the function and successively apply the derivatives to approximate the function. So this was the example 4.1. Do you have any question about example 4.1?
No.
No. Okay. Okay, if not, then let's move to this example 4.2. But before example 4.2, as a final result uh, uh, for this example 4.1, the different approximations have been represented over here graphically. So this function varies like this, okay? The original function varies like this, but its relative approximations vary in different manners. And as you can see that from the 0th order to the first order, you can see that gradually the error is uh, reducing, is reducing. So as we can expect from this function. Okay, next is the example 4.2. In example 4.1, we use the a simple polynomial function which introduces the exact result after some certain number of iterations. However, for some other functions such as the trigonometric function, we can never get the exact solution from the Taylor series. So we can get the solution, uh, a better and better solution by introducing more and more terms of the Taylor series. So in this case, it has been asked that in use the Taylor series expansion from n is equal to 0 to 6, which means that we have to go from the 0th to the 6th order Taylor series expansion gradually to approximate the value of cosine x at this value pi by 3. Okay. So now you know that. I think you can say that why do we need to do that? Well, of course, uh, we don't need to do that, but just for the illustration of the method, because we know that cosine of pi by 3, that is cosine of 60 degrees, 0.5. Everybody knows that, but the true value we already do. But let's see how the method works. Okay, so cosine pi by 3, and basically in this chapter we are looking at the concept of the error. So we can see that how the truncation error works. So on the basis of the value of x at x is equal to pi by 4. So the what is the main idea in this problem? Just like in the previous case, it was said that the value of the function at x is equal to 0 was given. Find the value of x, where find the value of function at x is equal to 1. In this case, it has been said that the value of this function at x is equal to pi by 4 is known. Okay, suppose we know that the value of x is equal to pi by 4. Uh, then find the value of at x is equal to pi by 3. So in this case, the interval will be then equal to pi by 3 to pi by 4. Okay, apart from pi by 4 to pi by 3. So that means we will go from pi by 4 to pi by 3. So which means that the difference between them is pi by 3 minus pi by 4 is equal to pi by 12. Okay, so the value of h we will take as pi by 12. So just remember the formulation of the Taylor series, and then you can apply this concept. So first of all, let's find the true value. So of course, true value, we already know that from our knowledge that it is 0.5. And then we can use this true value for calculating the true error, or in this case, the true percentage error. Okay, so the 0th order approximation will be equal to the value of the function, okay, at the given point, the value of the function at the given point. So At the given point is pi by 4, that is 45 degree. And then for 45 degree, we know that cosine can be approximated at as like this 0.707106,781. And then of course there will be infinite number of digits over here. So this is the zeroth order approximation. So in fact, this is already the answer, but of course it is an approximate answer. One part of the whole, the answer of the whole problem. So by using the percentage relative error, so we can find that the percentage relative error is minus 41.4%. So how we calculate the percentage relative error? It is the true value minus the approximated value divided by the true value multiplied by the 100%. So it will be minus 41.4%. So here we can see that the zeroth order approximation gives us a value which includes a true error of minus 41.4%. So just for the illustration purpose, here I am using the percentage relative error. Okay. In the previous example, I could have also used the percentage relative error, but here over there I use the true error. So whether you use the true error or the percentage relative error, the idea is the same. Okay. Uh, but more standardized way is to use the percentage relative error, okay, for the comparison purpose. Uh, Next is the first order approximation. So in the first order approximation, we actually need to calculate the first derivative. So the derivative of cosine x is minus sine x, and x is equal to pi by 4 or 45 degrees. So it will be same, but in the, of course, it will be now minus 0.707. So the first order approximation will be then equal to this. Okay. So here you can see that this is the answer from the previous zeroth order approximation minus the first order derivative multiplied by the value of h. Okay. And actually it is divided by 1 factorial, but 1 factorial is just 1. So that is okay, if you even if you don't write it. So it is pi by 12 is the value of h. So in this case, it gives us the value of 0.52. Okay, after you will calculate 0.5219. And then by the same formula before for the percentage relative error, you can see that the percentage relative error decreases to minus 4.4%. So in this case, you can see that the value is converging very quickly towards the true value. And now very quickly, the second order approximation is f prime of x is equal to minus cosine of x is equal to minus 0.707, because for the second order approximation, we need the second derivative. Yeah, here I think I made a mistake over here. It should be f double prime of x. Yeah, second order. Okay. Yeah, f double prime of x. So it will be minus cosine of x, because in the first derivative was minus sine of x. Yeah, it was minus sine of x. So it's further, one further derivative will be minus cosine of x. Okay. So minus cosine. So minus cosine of x is same as like its value, numerical value is this. So now what we can do is in order to write the full, instead of writing a full Taylor series, what we can use is that, what we can do is that we can use this value previously calculated and then add the additional term in that approximation. So which is the this term divided by a second order derivative divided by the 2 factorial into h square. So this is pi by 12 is h square. So it is 0.4977. So in this case, the percentage error is 0.449%. So you can see that now the value is less than 1%, is close, sorry, almost like 99% accurate in the second order approximation. Okay. So the question actually asked us to find the Taylor series expression from n is equal to 0 to 6. Okay, so I have illustrated it for the with the detailed calculation for the zero, first, and second order approximation. So the same process can be performed for the third, fourth, fifth, and sixth order approximation. And then that process can be summarized in this tabular format. So this table you can calculate from Microsoft Excel. Okay, so maybe I can show my screen. Okay, can you see the Excel sheet?
Yes.
Yes.
Okay. So in the Excel sheet, maybe you can, yeah, I can try to make it big. So in the Excel sheet, you can first create a column 0, 1, 0, 1, 0, 2, and then you can create a table for the derivatives. Okay, so in this case, the function is the cosine of x. So its derivative will repeat after 4 entries. Okay, so first it is the cosine of x, then minus sine of x, then minus cosine of x, and then sine of x. Okay, and then it will again become cosine of x. So after every 4, the values will repeat. Okay, so therefore you need to enter these 4 values, and then you can copy these 4 values at the same. So the values you can calculate like this. So you can see that the cosine pi by 4. Okay, so in Excel you can represent pi by pi function, and followed by 2 empty parentheses, and then divided by 4. So in this case, you will calculate the cosine, and then sine, and then minus cosine, and then sine. Okay, so the values will be repeating. The next will be uh, uh, the next column is for the Taylor series terms. So Taylor series, Taylor terms. Okay, and then this is the Taylor series. So in this case, so the next term will be the Taylor series. Okay, so this Taylor series you can calculate by using this first uh, term. Okay, divided by the factorial. Okay, for the factorial there is fact function, FACET fact function in, and then multiplied by the, and then you will multiply it by the pi by 12, which is the value of the h. Okay, so in this case you can formulate it over here, and then each term will be calculated. Okay, so that will be the Taylor term. So that means in this case the Taylor term for the first order will be this, and then this will be the second term, and this will be the third term, this is the fourth term. So the answer is actually the sum of these terms. Okay, the answer which is given in this Taylor series, it is the sum of these terms. So the first term is this. Okay, there is only one term, but here there are now 2 terms. So now these 2 terms are the sum of these 2 terms. So sum of sorry, it is so this value is the sum of this value over here and plus this. Okay, similarly this value, the third one, is the sum of the previous value plus the additional term, and then this value is the sum of this previous value plus this additional term. And here you can see that the values are gradually converging over here. And in the last sentence, the column, I have calculated the percentage relative error. Okay, percentage relative error. So for minus 41.5, minus 4.3, 0.4, and then so on. And then in the end, you can see that the relative error becomes much lower. Okay, so in this way, then starting from the 0th to the 6th order, or even for any order, you can calculate the values. Mhm. So now back to the PowerPoint. So you can see the PowerPoint now, right? Mhm. Can you see this PowerPoint?
Yes.
Okay. So in this way, then the results have been tabulated. So this is how the Taylor series approximations will work. Okay, with that, we can look at one more example. Uh, so in the previous case, now in the first two examples, I illustrated how we can calculate the Taylor series approximations for different types of functions. So in this example, we will see the effect of the non-linearity and step size on the Taylor series approximation. So figure 4.4 is a plot of the function fx is equal to x power m. So this is the figure 4.4. So x power m. So where m can have different values. So here we have chosen four values of m. M is equal to 1, m is equal to 2, m is equal to 3, and m is equal to 4. And you can see that starting m, more the value of the m, more non-linear the function is. Okay. So you can see that for m is equal to 1, the function is linear, but m is equal to 2, the function is gradually transferred towards non-linearity. So we want to see the effect of non-linearity on the Taylor series approximation by this. So for m is equal to 1, 2, 3 over the range from x is equal to 2, the values have been plotted. And notice that for m is equal to 1, the function is linear and as m increases. So apply the first order Taylor series, okay? So only up to the first order Taylor series to approximate this function for various values of the exponent m and the step size h. So this is how it has been calculated. So we have to just apply the first order Taylor series. For the first order Taylor series, so we have this, okay, the Taylor series. So for the first order Taylor series will include only the first two terms of the Taylor series, okay. And here you can see that this is the derivative. So for example, if we have this function x power m, its derivative will be m x power m minus 1 and times h, okay. And h is 1 in this case, because if we assume that x is equal to 0, then we can take h is equal to 1 in this case. And then, of course, when the Taylor series is there, if we are taking the Taylor series, and a Taylor series is an infinite series. There is the infinite number of terms, but we are only taking the first two terms. So then what are the remaining terms? So the remaining terms are called as the remainder. So what is remaining over here? So we can use the first two terms to approximate the function, and the remaining terms to calculate the remainder or the error for the function. So the remainder over here we can use for calculating the error. Okay, so in this case, then we can see that the Taylor series yields, if let's take for m is equal to 1, okay, that means this curve, okay, for m is equal to 1, what is the situation? So for m is equal to 1, the Taylor series yields the value of 2, and the remainder is 0. If we apply these values over here, remainder is 0. So in this case, you can see that when the function is linear, the first order Taylor series produces the exact value, okay, when the function is linear. So this is the conclusion. And for m is equal to 2, so for m is equal to 2, the function is now non-linear, but it is a non-linear of the order 2. So in this case, if you will apply the first two terms of the series, Taylor series, the value is 3. The original value is 4. The original value is 4. And the Taylor series also illustrates that the remainder is 1. So now we can see that the first two terms of the Taylor series uh, introduce the error over here in the nonlinear function, okay? And the error will gradually increase For m is equal to 3, the original value is 8, the approximated value is 4, and the Taylor series accurately calculates the approximate error in over here. So, but you can see that more is the nonlinearity in the function, and more is the error. Okay, so here in the previous case the error was 1. This in the current case the error is 4. So you can see that there is a discrepancy that can be determined exactly from the Taylor series. But the thing is that in this case, the discrepancy we can determine exactly, because we know that the discrepancy will be 4, but that discrepancy was determined exactly from the Taylor series. But of course, this is true because we are only investigating the kind of monomial function. And for m is equal to 4, the actual value is 16 and the calculated value is 5. So actual value is 16, calculated value is 5, which is very much different. Okay. But of course, in this case, the calculated value of the um, remainder is 11. So which we can exactly calculate from the Taylor series. Okay. So having said this, you can say that on the basis of these 4 cases, we observe that R1 increases as the function becomes nonlinear. So, which means that our conclusion is that when the function becomes nonlinear, the error from the function in the calculation increases. And furthermore, R1 accounts exactly for the discrepancy. So this is because this equation is a simple monomial with the finite number of derivatives. So this permits a complete determination of the Taylor series remainder. Okay. So with this, then we can also see that for m is equal to 4 and observe that how R1 changes and the step size h is varied. So if you just include the values of h over here and calculate the remainder in terms of the values of h, so we can see that uh, the remainder can be the remainder can be represented as 6h square plus 4h cube plus h4. Okay, so that means in terms of the step size. So this is the effect of the step size. So in this case, if for example, if we say that if h is relatively small, so we can approximately say that R is proportional, that is the error is proportional to the square of the step size, to the square of the step size. For example, if h is relatively small, so we can ignore the second and the third terms, and then we can say that the R is approximately uh, proportional to the value of the step size h. So this is the such illustration on the log plot. Okay, when the log plot, then the second order terms will be the straight lines. Okay, so this is how you can represent this as well. Comparison of the exact value of the function f of x is equal to x power 4 in the first order Taylor series approximation. So finally, the conclusion is that this leads to the conclusion that the discrepancy will decrease as h is reduced. So also at sufficiently small values of h, the error should become proportional to h square. That is, as h is halved, the error will be quartered. So this behavior is confirmed by the table 4.2 and figure 4.5 later on. Okay, so I stop at this point. No, and there is some more explanation for this error as well, but you can read it from here. And then in the next class, we will start from this point, error propagation. So do you have any question?
No.
No.
Okay, all right, then thank you very much.
Thank you too.
Thank you.
Goodbye.
Thank you. Goodbye.
Bye-bye.
Goodbye.
Bye.
Goodbye.
Goodbye.
Goodbye.